Okay, so hello and welcome back. So now let's talk a little bit about miscellaneous exercises on chapter 1. Miscellaneous exercises on chapter 1. Okay. So question number 1 is, let f from R to R be defined as f of x is equal to 10x plus 7. Now you want to find the function g. You want to find the function g from R to R such that g of is equal to f of g is equal to I of R. Now what that means is that what they mean by this is that you simply want to find the inverse of f, right? Now, and the reason why that is, first of all, I didn't know, I mean when I read this question, I didn't understand it. So I had to take a look at the solution and do the solution one complete time, nearly one complete time. And then what I found out was that basically, so here they have written g of f is equal to f of g is equal to I of R. What that means is that in the previous videos, we said that it's basically if you have some function, for example, from x to y, now you can find the inverse of f as, for example, f inverse as a function from y to x. And in order to make sure that basically, now of course first you need to make sure that basically f is basically 1 1 and f is basically 1 1 and onto. So once you know that f is 1 1 and onto, then you know that f is invertible. Now once you know that f is invertible, then you define some function f inverse to be the inverse of f. But then you need to check whether the function that you have defined is actually the inverse of f. And so the test that you can perform for that is that you need to make sure that f inverse of is equal to basically the identity function on the domain of f, I of x. And you need to make sure that f of f inverse is equal to I of y. Which is basically, and this is supposed to be capital Y, of course. So if you can make sure that these two are the case, then basically what that means is that basically then f inverse is the inverse of f. Now the statement that we have over here, as you can see, that is equal to g of f is equal to basically I of R, which is basically the domain of f. And f of g is also I of R, which is the range of f. And so and for the same reason they have combined these two together and written this as g of f is equal to f of g is equal to I of R, right? So that means that you simply want to basically find the function g, which is the inverse of f, and that's basically all that you want to do. I mean, there is nothing more. Now, so first, the first step is to make sure that f is first of all invertible. To make sure that f, to basically to make sure that f is invertible, you need to make sure that that f is injective and surjective. Meaning that you need to make sure that f is basically bijective. You need to make sure that f is bijective. Injective, as you know, another name for injective is 1, 1. And surjective is onto. So if a function is 1, 1 and onto, you can call it a bijective function. Now, in order to test for basically for 1, 1, you can imagine that you can assume that basically some f of x1 is equal to f of x2. So you can assume that let us assume that f of x1 is equal to f of x2, where basically x1 and x2 belong to the domain of the domain of f, which is R, right? Belong to this domain. Now, if f of x1 is equal to f of x2, that implies that basically f of x is equal to 10x plus 7, so f of x1 becomes 10x1 plus 7. 10x1 plus 7. And f of x2 is equal to 10x2 plus 7. Now, if you simplify this a little bit, you'll get x1 is equal to x2, which means that basically you have assumed here that f of x1 is equal to f of x2, and that implies that x1 is equal to x2, which means that f is basically 1, 1, right? Now, to show that f is onto, what you can do is that you can argue that let y be an arbitrary element of the range of f of x. So if y is an arbitrary element of the range of f of x, then what I can do is that then of course y is equal to f of x. F of x is equal to 10x plus 7, right? So f of x is equal to 10x plus 7, and since y is an arbitrary element of the range of f of x, then you can say that that is basically y is equal to f of x. Now, since y is equal to f of x, you can write y is equal to f of x is equal to 10x plus 7. So that means that y is equal to 10x plus 7, and 10x plus 7, if I find basically, if I solve for x, I will get 10x is equal to y minus 7, or that means that basically x is equal to y minus 7 divided by 10, right? Now here we said that f of x is equal to 10x plus 7. So since f of x is equal to 10x plus 7, then you can say that instead of x you can write f of y minus 7 divided by 10. That is equal to 10 times this, which is basically 10 times y minus 7 divided by 10, and add 7 to that. So you can simplify these two and simplify these two, you'll get a y, which means that f of y minus 7 divided by 10 is equal to y, which means that for every y belonging to, for every y belonging to the codomain of the function, there exists an x equal to y minus 7 divided by 10 belonging to the range belonging to the domain of the function, such that f of x is equal to y, which means that now the same sentence, the same statement, I can write it as in simple English, I can write it as for every y. What this means is that for every y belonging to the codomain of the codomain of f, there exists an x which is equal to basically y minus 7 divided by 10, that there exists an x such that basically f of x is equal to y. That is, every y belonging to the codomain of the function is the image of some element in the domain of the function. In the domain of the function. Therefore f is onto. Now, the way that I have made this, come to this conclusion, that is of course important. Here we have f of y minus 7 divided by 10 is equal to y. And here, basically what we are saying is that what we have is that f is a function from R to R, right? So we have f is a function from R to R, right? So what I'm saying here is that for every y that belongs to this set, which is your codomain, there exists for each of these y's, there exists some y minus 7 divided by 10 that belongs to this set, and then you can use that element as a pre-image to get to the other element in this set. And of course you need to use the properties of, well, all numbers and the different sets in mathematics and all of those things. You have to put them together in order to make sure that that this element actually does exist in the domain of the function, meaning that, for example, if in this case, if I had f is a function, for example, from n to r, or if I had, for example, f is a function from n to n, then suppose that, and I got the same basically rule over here, then of course the function would not be onto, because, for example, suppose that for example y was equal to 2, for example, right? So for y is equal to 2, you need to have this element in the domain of the function, which is 2 minus 7 divided by 10, which is equal to negative 5 divided by 10, which is equal to negative 1/2, which does not belong to n, right? When negative 1/2 does not belong to n, so then the function would not be onto. But since I'm working with the set of real numbers here, whatever you got here, then whatever you have here is a real number, then you put that real number here, subtract the 7 from it, you still have a real number. Divide that real number by 10, you still have a real number. So that exists in the set of real numbers, and therefore every element that you have here is the image of some element here, and therefore your f is basically, the function is onto, right? So now what we have shown is that basically f is 1, 1, and also f is onto, and therefore f is invertible. F is invertible, right? So now that we know that f is invertible, let's define some function g, for example, which is the inverse of f, and then we need to make sure that the function that we have defined is actually the inverse of f. Right? Okay, so now that we know that f is invertible, so now what we can do is that you can basically using the function that we found here. So we said that for every y that you can find in the codomain of f, there is some y minus 7 divided by 10 that gets you to that y. That means that you can use this as the inverse of f in order to use it as the inverse of f. I guess my statement didn't make any sense. What I mean is basically if suppose that, for example, this is the domain of the function, and this is the range of the function, right? Now this is f that goes from the domain all the way to the range of the function. So if I assume that basically y is some typical or some arbitrary element in the codomain of the function, there is always an element y minus 7 divided by 10, and if I give this to f, that it basically takes me to y, right? So from here, what I can do right now is that I can define a function, for example, instead of f, for example, let's say g, and of course if I give this y to g, it gives me y minus 7 divided by 10. That means that I can say that let us define, for example, g of y as y minus 7 divided by 10. And of course g is a function from r to r, because f was a function from r to r. So this was r and this was r, so then g becomes a function from r to r, right? So what that means is that now we need to make sure that this function is actually the inverse of f. Let us define g of y as the inverse of f of x, right? Now, to basically to make sure that basically that g is the inverse of f, you need to show that basically GOF of x is equal to x. GOF of x is equal to x. I cannot tell you why that is, because it gets into a whole bunch of explanation, and we have done the explanation in one of the videos in this chapter, in this course. Otherwise, even if I were to tell you, I wouldn't know where to start, really, because it goes into a couple of definitions you have to put together, and you have to talk about them and put them in a certain order, and then you will come to the exact same conclusion, that if GOF of x is equal to x, which implies that GOF is equal to I of x, the identity function on the domain of f, and also FOG of y is equal to y, which implies that FOG is equal to I of y, right? Which means that FOG is the identity function on the domain of f. Then you need to show this, and if you can show this, then that means that implies that basically G is the inverse of f, right? So let me make a screenshot here, and then we will create some other some new space here, and we will continue over there, because we actually have run out of space here. 2:30. Okay, so we said that basically f was a function. We said that f was a function from R to R, and it was defined as f of x is equal to 10x plus 7. 10x plus 7. And we defined g of y, we defined g as a function from R to R, and g of y we defined it as some function as y minus 7 divided by 10, right? And now if I calculate GOF of x, or basically GOF is the same thing as g of f of x. Now g of f of x is the same thing as, well, 10x plus 7. 10x plus 7 minus 7 divided by 10, which gives you an x. 10 and 10 will cancel out, you will get an x. Which means that GOF is the identity function on the domain of f. That means that basically GOF is the identity function on the set that is the domain of X. Domain of X. Domain of F, I'm sorry. The domain of F, right? So G of F is equal to I of X. Now if I calculate F of G is the same thing as F of G of Y. Now F of G of Y is equal to 10 times this whole fraction, or this whole function, which is y minus 7 divided by 10, and add a 7 to that, and these two will be cancelled out, and you will have y. That means that f of g is the identity function on the codomain of f, right? On the codomain of f. And what that means is that then g is the inverse of f. Okay, so that was question number 1. Hence the required function g is basically a function from R to R defined as g of y is equal to y minus 7 divided by 10. That was question number 1. Okay, so the question number 2. Question number 2, we have basically let f be a function from w to w be defined as f of n is equal to n minus 1 if n is odd, and f of n is equal to n plus 1 if n is even. So let me write it this way. So it's equal to f of n is equal to n minus 1 if n is odd, and f of n is equal to n plus 1 if n is even. I want to show that f is invertible. Show that f is invertible. Find the inverse of f. Find the inverse of f. And here w is the set of all whole numbers. Okay. This basically is the set of whole numbers. Okay. Okay, so now basically this example is a little bit technical, you know, meaning that you get different cases, and the reason why that is that basically you have a function that has two clauses. So and for the sake of simplicity, what I'm going to do is that I'm going to change these to x, because I get confused when I'm dealing with n and so on and so forth. I just cannot, it would be harder for me to understand everything. So I'm just going to change everything to x so that I can work with them. So so this is f of x as far as we are concerned, x plus 1, x minus 1, and here x is odd, here x is even. Okay. Now, so basically you want to show that you basically have a function from the set of whole numbers to the set of whole numbers, and the function is defined as f of x is equal to x minus 1 for odd x's and x plus 1 for even x's, right? You want to show that f is invertible, and you want to find the inverse of f. So in order to show that f is invertible, of course you need to show that f is 1, 1 and onto. You need to show that f is 1 1 and onto. Okay, so in order to do that, so to show that basically, to show that f is 1 1, what you need to do is that basically you need to show that for, if you take some f of x1 is equal to f of x2, for example, then that implies that x1 is equal to x2. So what I'm going to do is that I'm going to assume that so let us assume that for example some f of some x1 is equal to f of x2 for x1 and x2 belonging to w, for example, right? So if that is the case, then we need to use this assumption in order to show that x1 is equal to x2. Now, there are a few cases here, meaning that you could have a couple of cases. You could have basically x1 and x2, so x1 could be odd, x2 could be even. So there are a couple of cases. So let's say that, for example, case 1, you can say that, for example, x1 is odd, for example, and x2 is even. Case 2, you can say that, for example, x2 is even and x2 is odd. Case 3, you can say that x1 and x2 are both, for example, even. And case 4, you can say that x1 and x2 are both odd. And we need to take care of these 4 cases one by one. Now, case 1, we are saying that x1 is odd and x2 is even. Now, if I assume that f of x1, the assumption that we had was f of x1 is equal to f of x2. Is equal to f of x2. Now, if x1 is odd, then what that means is that then f of x1 would be x1 minus 1. F of x1 would be x1 minus 1. And if x2 is basically even, then f of x2 would be x2 plus 1. So that would be x2 plus 1. Which means that x1 minus x2 is equal to 1 plus 1, which is equal to 2. Now, over here, what we have is that x1, which is an odd number, x2, which is an even number, and the difference between these two numbers has become an even number. So if you examine this a little bit, you will see that this is actually not possible, because suppose that you have some odd number, for example 7, and you subtract from that from some even number like 4, you will get a 3. You have an odd number, for example, let's say 9, and subtract from that an even number, for example 2, you will get a 7. An odd number, for example 13, and subtract from that an even number 4, you will get a 9, for example, and so on. So you can see that all of these numbers are odd numbers. That means that it's not possible that you subtract an even number from an odd number and you get an even number. It's just not possible. So this is impossible. This is an impossible case. That is basically the first case. The second case that we have is basically case 2, which is x2 is even and x2 is odd. So case 2, we have x2 is even and it's actually, this is supposed to be x1. x1 is even and x2 is odd. And basically what I'm assuming here is that basically f of x1 is equal to f of x2. Now, if x1 is even, then f of x1 becomes, if x1 is even, then f of x1 becomes x1 plus 1. x1 plus 1. And if x2 is odd, then f of x2 is equal to x2 minus 1. x2 minus 1. Which means that x1 minus x2 is equal to, again, negative 1 minus 1, which is equal to negative 2. So what we have here is that we have an x1 is even, x2 is odd. This is an even number, this is an odd number, and you are subtracting an odd number from an even number and you're getting some even number. Well, of course it's negative. That's another story, but it's an even number. Which means that, for example, let's say that you have some number like, for example, 8, which is an even number. Subtract from that, for example, 7. You will get a 1, which is an odd number. Let's say that you have another even number 16. Subtract from that an odd number 9, and you will get a 7. 7 plus 9 is equal to 16. So that's an odd number. Let's say that you have another even number, for example, 18, and subtract from that a 9, you will get a 9. Again, an odd number. Or, in order to get the negative side, you can say that, for example, you have an even number, for example, 2, subtract from that, for example, an odd number 7, you'll get a negative 5. It would still be an odd number, but a negative odd number. Which means that this case is actually not possible. It is impossible. This case is impossible. This case is impossible, right? Which means that basically, both x1 and x2 must be either even or odd, meaning that, well, since basically these two cases are not possible, then either we have this case number 3, or we have this case number 4, right? So case number 3 is saying that basically both x1 and x2 are even, and case number 4 is saying that x1 and x2 are both odd. So that means that, which means that basically both x1 and x2 must either be even or odd. So now let's see what happens if we try case number 3. If I try case number 3, so case number 3 here is that I'm assuming that f of x1 is equal to f of x2. So what happens is that both, in this case, both are even. So even we have here x plus 1. So x1 plus 1 is equal to x2 plus 1, which means that x1 is equal to x2. So that means that Here I'm assuming that f of x1 is equal to f of x2, and here we are saying that x1 is equal to x2, right? Which means that basically f is 1, 1. Which means that f is 1, 1. On the other hand, if I try case 4, what happens is that f of x1 is equal to f of x2, and case number 4 is x1, x2 are both odd. Both odd means x minus 1. So that is x1 minus 1 is the same thing as x2 minus 1, which means that x1 is equal to x2. And in this case also, f is 1, 1. F is 1, 1. So that is basically to show that basically f is and that is to show that f is 1, 1. So you can say that therefore f is 1, 1. Now in order to show that basically f is onto, what you need to do is that you need to show that basically every element of the codomain is the image of some element in the domain of the function, which is a little bit tricky in this case because you're dealing with even and odd numbers, but that's not a problem. We will break it down and we will understand it. Okay, so now in order to show that f is onto, so basically the outputs of this function f, basically we have this function f over here, which is f of x is equal to x minus 1 and x plus 1 for odd x's and even x's. So we have f of x is equal to basically x minus 1 and x plus 1. X plus 1 for odd x's, and for even x's. Right? So what you need to show here, and of course you can see that when x is odd here, then f of x is going to be even here. So here basically you have an even output, even f of x. Because when you have an odd number and when you subtract 1 from it, when you subtract the 1 from an odd number, you will get an even number. And so f of x is going to be an even number. And when you have an even number and you add 1 to it, you will get an odd number. That means that you will have odd f of x's here, right? So you need to show that basically if you want to show that basically f is onto, that means that basically when you have basically your function f here, so this is your domain and this is your codomain, and here you have some even f of x's and you have some odd f of x's, right? And you are basically, this is the set of whole numbers, so this goes from 0, 1, 2, 3, 4, and so on and so forth. That's the set of whole numbers. That's a collection of some basically even numbers, some odd numbers. And all of these even numbers and odd numbers are output here by f of x. So you need to show that basically every even f of x is the image of every even f of x is the image of some element here, and every odd f of x is the image of some element here. And in order to do that, basically you need to, and basically if you can show that, then that means that basically every element in Y, or every element in the codomain of the function is the image of some element in the domain of the function, and that means that every element is in Y is basically covered. And so if every element is in Y is covered, then that means that then your function f is basically onto, right, or surjective. Now, since I need to be talking about even numbers and odd numbers in mathematical terms, I cannot just say even numbers and odd numbers. I have to denote them by some notation. And the notation that I can use is that I can write basically, I'm going to denote 2r plus 1 as I'm going to denote odd numbers by 2r plus 1 for some r belonging to the set of, for example, whole numbers. And I'm going to say that 2r, I'm going to denote basically even numbers by 2r for some r belonging to the set of whole numbers. Now what happens here is that basically, for example, you can see that if suppose that, for example, my r is, for example, this is my r, and this is, for example, 2r plus 1. Let's say that r is equal to 0. Your output becomes 1, or 2r plus 1 becomes 1. That's r is equal to 1. Then you will get a 3. Let's say that r is equal to 2. You will get a 5, and so on. So 1, 3, 5, 7, and so on and so forth. So these are all odd numbers. And let's say that basically you have your r here and you have 2r here, and if r is equal to 0, you'll get a 0 here. And if your r is equal to 1, you'll get 2 here. If your r is equal to 2, you'll get 4 here. If your r is equal to 3, you'll get 6 here. So 0, 2, 4, 6, 8, and so these are all the even numbers. So this way we will be able to talk about these numbers and use them in algebra, right? Otherwise I cannot write the word, for example, even and odd in algebra. That doesn't simply work for us. So now I need to show that every odd number, which is 2r plus 1, is the image of some element in the domain of the function, which means that basically when the output of the function is odd, of course you can see that here f of x is odd, and that's basically where all of the odd where all of the odd f of x's come from x plus 1. So if I write f of x is equal to x plus 1, and I know that basically x is supposed to be even here, and so the output is going to be odd. Then let's say that, for example, let's take some arbitrary f of x here. There's some arbitrary member of the set f of x as y, for example. So then y would be equal to x plus 1, and then x would be equal to y minus 1. That means that if I write the same relationship as f of x, but instead of x, if I write y minus 1, I will have basically, instead of x, I write y minus 1, and we have a plus 1 over here. I'll get a y. That means that f of y minus 1 is equal to y. So now these y's are all basically are all of course odd f of x's. These are all odd numbers. Now I can say that, and so I can say that every odd number y that I can find in the codomain of this function is going to be the image of some y minus 1 in the domain of the function. Or if I denote these y's with 2r plus 1, so basically you can see that I have a y over here, and the pre-image of that y in the domain of the function is y minus 1, meaning that any y that I want to get to in the codomain of the function, I have to be looking for y minus 1 in the domain of the function. Which means that if I have 2r plus 1 in the codomain of the function, I need to have 2r plus 1 minus 1, which is the same thing as 2r. Which means that any 2r that I input into this function is going to give me some 2r plus 1, which is of course going to be an odd number. Which means that I can write that it is clear that any odd number 2r plus 1, any odd number 2r plus 1 in the codomain of f is the image of some 2r in the domain of f. Right? So that we know. So it's clear that any odd number 2r plus 1 in the codomain of f is the image of some 2r in the domain of f. And then I can do the same thing for the even numbers as well. Meaning that I can say that basically over here I know that the output of my function, or all of my f of x's, are even, right? And we are talking about this class here, meaning that I can write f of x is equal to x minus 1. Here x is odd, the output is going to be even. Now some arbitrary output of this function, if I take it as, or some arbitrary member of the range of this function, if I take it as y, then y is going to be equal to x minus 1, which is x is equal to y plus 1. Which means that if I write, instead of f of x, if I write basically f of y plus 1, that's going to give me y plus 1 minus 1, which is equal to y. That means that basically any even f of x that I can find in the codomain of this function, there is some y plus 1 in the domain of the function that is the pre-image of that even f of x, or that even y, right? Now here we are denoting all the even numbers by 2r. So that means that we said that any y, I have to, the pre-image for that is y plus 1. So any 2r, the pre-image for that would be 2r plus 1. Which means that here then I can write and also basically any even number 2r in the codomain of f is the is the image of some 2r plus 1, is the image of some 2r plus 1 in the domain of f, right? So basically every number that we have in the codomain of the function, whether they are even or odd, so this way they are all covered, and so you can say that therefore basically f is onto or surjective. Now what that means is that and therefore you can, since basically f is basically let me take a look at these things here. Okay, so now here we said that basically so here basically we said that, use another color here, so here we said that f is 1 1. And now we know that f is 1 1, and also f is onto. That means that f is bijective. F is bijective, and therefore f is invertible. Now let's find the inverse of f. Now to find the inverse of f, you need to define the inverse of f. Now to define the inverse of f, f, we have, so f was basically this function here, which was basically f of x is equal to x minus 1 for odd x's, and x plus 1 for even x's. So what that means is that if I have f of x is equal to x minus 1 for odd x's and x plus 1 for even x's, so what that means is that if I now we said that we argued before that here f of x is not odd but even, but here f of x is odd, right? Now if I take some, basically if I denote some even f of x as y here, so if I have, let's say that I have f of x here is equal to x minus 1, and this is going to give me all of these even f of x's. Now these f of x's, if I denote them as y, that gives me y is equal to x minus 1, and x is equal to y plus 1, which ultimately means that basically f of y plus 1 is equal to y. Or you can basically define the inverse of this function as f of y is equal to y plus 1, right? And that is because you can see that this function, this goes from, let's say this goes from x to y, and let's say that you have some x here, say that you have some x here, and here it gives you some y, for example. So f is a function that goes from x to y, and it maps all of these lowercase x's to these lowercase y's. Now over here, whatever the value of x, you are subtracting a 1 from it. And if I want to find the inverse of this function, if I denote that by, for example, if I denote that by g, for example, g of y is equal to y plus 1. So if I denote that by g has to be a function that, so here basically the goal that we have here is that the x that you start with, you have to end up with the same x, meaning that your x goes into f, and then through g you come back to the same x. Now f is subtracting a 1 from your f, subtracting a 1 from your x, right? And that becomes y. And then whatever that y is, g has to add a 1 to your to the value of y, so that you end up with the same value of x that you started with, right? So therefore I can say that when f of x is equal to x minus 1, the inverse of that becomes, for example, some function like g of y, which is equal to y plus 1. That is basically one part of the story. So I write this over here, g of y is equal to y plus 1. And this is for the first part. Let's call this 1, and this is for 1. And let's call this 2. Now, to take care of the second part, you can say that basically, let's say that f of x is equal to x plus 1. If I denote these f of x's by y here, y is equal to x plus 1, which means that x is equal to y minus 1, right? X is equal to y minus 1. That means that ultimately f of y minus 1 is equal to y, which means that if I denote the inverse of this function by some, for example, g of y, that is going to be equal to y minus 1. And the reason for that is simply, and you can of course find the formula from here, or the algebraic form of the function from here, and you can see that here, whatever the value of x, 1 is added to it, and then this function, which is supposed to get you back from y to x that you started with, then this function is subtracting a 1 from the same y, and it will take you to the same x, right? So then I can say that g of y is supposed to be y minus 1 for the second part, for 2, right? So then I can write over here, what I can write is that basically, let us define basically g of x as basically y plus 1, and of course you do appreciate the fact that here basically f of x is even, right? So that means that this is the output of this function, which becomes the input of this function. So here, of course, y is supposed to be equal to, this is for even y's. And over here, g of y is equal to y minus 1, which is then, on the other hand, which is for odd y's. Right? And the reason for that is that here your f of x is equal to, your f of x is odd, right? So since your f of x is odd and the output of this function is odd, then over here y has to be odd, because we got this formula for the second part, and so f of x, which is the same thing as y, has to be an odd number, and that becomes the input here. So this is for odd y's, y minus 1. So what that means is that then, long story short, you have this function here, basically defined this way, and G can be a function from, again, the same set to the same set, or basically actually the other way around, meaning that it has to be, I don't know where we were started with the whole story, from W to W. You have to go the other way around, of course, from W to W. So this is a function from W to W defined this way. So if I write G is a function from W to W as y plus basically G, this is supposed to be equal to y, of course. G of y is equal to y plus 1, y minus 1 for even y's and for odd y's. Now we need to basically hopefully you do remember the fact that in order to make sure that basically to make sure that let me actually end this video here, and we will continue the rest of this discussion in the next video, because I'm getting over 1 hour. So I'll end this video here, and then we will continue in the next video. Thank you.